Thanks, Amit, and thanks for inviting me here to give a group meeting, especially for what I imagine is probably an unusual topic for the meeting. Also, please, since it seems it's very nice to actually be able to give a seminar in person again, I now realize, though, that I can't read anyone's facial expressions, so please ask questions if you're confused, because I won't be able to tell otherwise. So this talk is going to be based on some work I did in a book written with Shoyeda, and based on work in collaboration also with Boris Hannon. And it's on trying to use ideas from effective theory to understand how neural networks work. So modern, thanks to advances in computer technology, modern AI systems come with many numbers of elementary components. Some of them have more than 1 billion components, and they're able to accomplish tasks that are at one point that are so exciting that at some points various philosophers have thought that only natural intelligences such as humans would be able to accomplish these tasks. And although von Neumann in this quote was really talking about quantum mechanics, we could imagine him making a similar observation about modern artificial intelligence systems. Many components of these systems tend to obscure their real nature, and it's very popular to say that they are just a black box beyond any scientific understanding. I also think, though, von Neumann would know that physics has a long tradition of finding simplifications in systems in the limits of a large number of degrees of freedom or elementary components. And so what I'd like to discuss in this talk is to see whether some of those tools can be applied in this setting. Before I do, though, let me first describe what I mean by AI or artificial intelligence. And rather than talking about some computer system or some type of technology, instead I just want to talk about functions and the way we describe functions. So some functions are easily described in terms of elementary operations, such as addition, subtraction, multiplication, division. For instance, here's an example of one. The identity function is quite simple. There's no elementary operations, so that one's really easy. We can also imagine talking about the elementary function, the exponential function, and assuming you don't know the value of e, one way of defining this function in terms of these operations is by its Taylor expansion. And here, as I'm sure is familiar, this involves just these simple elementary operations. We repeatedly multiply x k times in the numerator, then we divide by a repeated multiplication of the integers from 1 up to k, and then we sum terms for k going from 0 to infinity. And although it may seem like there's an infinity of terms here, for many purposes, it actually only takes a few terms to get a useful approximation. And the description, well, I guess everyone is on different screens here, and it's maybe more like a foot on this screen, but the point is that the description is rather compact on a slide. So in terms of these operations, we have, I guess you can think of it as the language or the programming language to describe this sort of function. And so we understand it, this is kind of analogous to what we mean by understanding it. On the other hand, there are some functions that really cannot easily be described by these elementary operations on any slide. So for instance, you can imagine a function that outputs 1 if the inputted image contains a depiction of a cat, and outputs 0 if the image, the inputted image does not contain a depiction of a cat. And it's clear that such function can exist. Humans, at least humans beyond of a certain age who have at least been exposed to cats can do it, but it's unclear how to represent this function using in the way we represented, say, the exponential function using these elementary operations. So this is the sort of functions that we're interested in or at least I'm interested in when I talk about AI, functions that are easy for humans to evaluate, but hard for humans to describe by these sorts of elementary operations.
Excuse me, what's the domain of that function?
What's the name of what?
What's the domain of that function?
Yeah, I see. Right. So if I'm being a little, I guess, abstract, but right, we could formalize this by talking about images that are, say, digitized on a computer have some number of pixels, sort of a certain size, or we could allow images to be different sizes. I mean, the details of that are not going to be important, but is the point I made confusing or about this?
No, not at all. I was just, I mean, when you said X, I assumed it was an element of a field or a ring.
Yeah, exactly. Okay, fair enough. I'll try to be more careful. Okay, great. So behind these recent exciting advances in AI that you may have read about in the news is what's called deep learning. And deep learning is as you can think of as a framework that uses artificial neural networks as an underlying model for AI. These models are loosely based on biological neural networks, your brain, and can be coarsely understood or to zeroth order, let's say, as a flexible set of functions built from simple components, which are called neurons, and parameterized by a large vector that I'll call theta. And this drawing is a graphical depiction of the way people typically represent networks, and we'll return to that in a bit. But for now, I want to throw away some of the details and just try and understand in the abstract how we would think about a general parameterized function and talk about how we can use a set of functions like this to learn that cat function that was undefined on a few slides ago. So here, the important point is that x is the input to the function, and theta is a vector of a large number of parameters that we use to control the shape of a function. So for this function to be useful for the task that we're interested in, we need to find a way to tune the high dimensional parameter vector theta. And typically in practice, what's done is as follows. First, we'll sample data from some sort of computationally simple initialization distribution. So often uses a Gaussian distribution or maybe a uniform distribution over some specified range, but something that's simple to sample from. And then second, we'll adjust the parameter vector in some way such that the resulting function that the network computes after the adjustments is as close as possible to the desired function that we're trying to emulate, like the cat function. And in general, this is called function approximation, and it's kind of a different way of finding a function to solve a given task compared to the way I specified before in terms of the elementary operations. Rather than programming it, we're adjusting a very flexible function some way until it's close and looks like the function that we're trying to, that we're interested in approximate, and that we're ultimately interested in. So typically to find these tunings, what we do is we fit the network using training data, which consists of many samples from the function or observed from the function at particular points for particular inputs and paired with their outputs. And we're only given access to these pairs, but we don't have, we often don't have access to the underlying function itself. And if we did, in some sense, know the expression for the function, then we wouldn't need to be doing this. So thinking back on that cat function before, we're handed a number of images of cats and not cats, and then their associated labels. But we're not told anything about the details of the function.
All right.
Yes?
Is there a precise way to see how distant the function that you are creating and the object that you want to get are? So some metric or some way to make precise these two squiggly lines of proximity?
Yeah, so there are a number of ways. I don't know that there's a number of ways, and often, I guess I will sort of say it in a second, but there are a number of ways, but often what you do is you define some way like that, and then you want to minimize that auxiliary objective, and that's part of this process called training. So you can think of, when we make these adjustments, we think of that as training, and we do so based on this data in some way, often involving defining a distance function or a loss. this whole collection of ideas often is called the learning algorithm. To your point, often the choice of learning algorithm, which I'll think of as including the definition of that distance or objective, as well as the procedure used to minimize or to minimize that distance. So all of that I'll think of as the learning algorithm. That choice is often as important for the success of this function approximation as the definition of the set of functions itself. So it's important to both be careful defining your network so that you get something nice, and also this procedure. And so our goal is to analyze that whole package of ideas together. So we want to analyze both the models themselves, and then we want to analyze the learning algorithm, which includes this distance function, and understand theoretically how they work, or how they're computing the function that we're interested in. So right now, everything has been very abstract and high level, and the reason for doing this is to just sort of talk about the sort of problems that you might have if you're just using a general set of tunable functions. So one way to see the sort of problems we'll encounter is by Taylor expanding the trained function around the initialized values of the parameters. So in this expression, it's still very schematic. That I've often the parameter vector is high dimensional, so I've ignored the fact that the gradient is a vector and the second derivative is a matrix, and so on. But schematically, I'm sure this makes sense, and also, yeah, as it would make sense for what I was saying, the derivatives are all evaluated at the initial value of parameters. So. But the point is, or one reason for doing this is that if we understood all the details, if we understood individually all the terms on the right-hand side of this expression, then we would understand the left-hand side of this expression. So the expansion made sense, and then we'd have a way of understanding the function that we're trying to analyze. So this is helpful because it outlines some problems that we'll encounter when we try to do this, when we try to think about analyzing this train function. So of course, in general, the Taylor series contains an infinite number of terms, and in principle, we would need to have a way of evaluating them all. So we would need not to use the expression that I had. We would need to know not just the output of the function at initialization, but also the output of various derivatives for the different inputs. And of course, whether or not these terms matter depends on how far the network has moved, and the difference between the initial and the final value parameters. But in principle, we need to understand which of these terms we need to include. Second problem is that since the initial parameters are randomly sampled from the initialization distribution, each time we initialize our network, we're going to get a different function f of x semicolon theta, and we need to determine the mapping from the initialization distribution over the parameters, which was simple, easy to sample from, to whatever happens when whatever the joint distribution is between the function and its various derivatives. So of course, remember each term in this expansion is a function of the different inputs, and so this Taylor expansion is really a random function of the input x, and this joint distribution may have some intricate statistical dependencies, and we would have to understand them in detail if we were to use this Taylor expansion method way of understanding the trained network function.
Question?
Yep.
Why is it okay to assume the function is differentiable, smooth, or do you need to say anything about it?
Yeah, so I mean, if it's not differentiable, then some aspect of what I'm saying might fail. You can pick networks where they're differentiable. You can pick for cases where they're not. Most of what I'm saying is true. I can point out the one thing that's not true anyway. I'm being schematic now to try and highlight how the analysis is going to go. But yeah, if there's what you're saying is true, that if the expansion doesn't make sense, then this method is not going to work. This method also seems, the way I'm presenting it right now, it doesn't seem very hopeful, right? Anyway, I'm pointing out a bunch of problems. So when we come back to that at the end, then.
I mean, I had the same question as Ibru. I mean, the function you presented, your cat function, is very discontinuous. And you're assuming F is analytic. And I had the same question about the domain of theta. If the domain of theta is cats and dogs, namely the very high dimension vector over the field of 2, then it's not clear to me why it should be continuous or differentiable or analytic.
Yeah, so the domain of theta is like Rn, or for some large n. I'm going to use n for something else, so don't connect that to n I say later. But it's just R to some power for however many parameters there are. And I'll explain that in a few slides when I get into away from the abstract part and more of the specifics. And what was the other part of what you said? I don't think
your example function was discontinuous, right? It was 0 or 1.
Oh, sure.
If we think of cats and not cats as regions inside some high dimensional vector space,
that's fair. We can.
Which I think is what you're doing.
Well,
then is theta is not of that nature. Theta is, as I think you just said, it's a vector in some high dimensional vector space.
Yeah, so for the 0 to 1 thing, right, we can relax that and make it output the probability that it's or the log odds that it's a cat versus not cat, and then it'll just it'll output the computer has some quantization and range issues, and actually those will be important, and I'll talk about them. But in general, I think you can think about that as the output, and then act with the sigmoid function at the end and take the max or something like that. So these issues actually are not going to be that important. So maybe I'll move on from them. But if you're unsatisfied at the end, please bug me about that. That's fair. Okay. So right. So distribution over random functions. We need to understand the mapping from the parameter settings to the distribution over the function and its derivatives. And also just to highlight, this is important because in practice, every time you put one of these functions on your computer for practical purpose, you resample the parameters data, and so it's important to understand whether the sampling is going to be typical or not, whether the particular instantiation of the function that you have behaves typically in the ensemble or doesn't. So these issues are important. And then the final problem in using the Taylor expansion, if we were to use it, if it were to make sense, is that the learned values of the parameters are the result of some sort of complicated training process. It involves defining a distance function, as was pointed out before. And in general, first of all, it's not necessarily unique, and it will depend on everything that's part of the problem. So it'll depend on the initial values of the parameters. It'll depend on the initial values of the function output and its derivatives. It will also depend on the details of how we choose to tune the parameters, what the learning algorithm is. And of course, it's going to depend on the training data. That's kind of the whole point. When we want to fit a function, we need it to, in order for it to fit to the data that we have, it has to depend on the training data. So determining analytically what this is must take everything into account. And often, I should say that although I won't be able to get into it in this talk, often these training processes or these learning algorithms are iterative. And so these are some sort of discrete dynamics and often highly nonlinear, and you have to solve a dynamics problem in order to plug in in order to compute the difference between the trained value of the parameters and the initial value of the parameters. So there's a lot of problems with trying to understand if we could solve all these three problems, right, then we would have a distribution over trained network functions. Now conditioned in a simple way on the learning algorithm and the data that we used. So let me make a few points. First, we started out by saying we want to analyze the train function. I'm now just kind of pointing out that actually we have a whole ensemble that we have to care about. And second, the conditioning on the training data sort of makes sense. it's what I explained on the previous slide. Even if we have a simple expression for the trained function, we'll need some way of inputting the data that we have into that. And so we have to condition on the training data. And similarly, the reason we're still conditioning on the learning algorithm is that you get different results depending on different learning algorithms that you use. So the difference between the previous slide and this slide is, in the previous slide, there's some complicated dynamics problem that we maybe have to solve. Here, we've already solved the dynamic. I'm imagining we've solved the dynamics problem. That's what the data star is. And the conditioning and learning algorithm is just, is something simple that tells you which particular learning algorithm you used, as opposed to leaving you to solve a complicated dynamics problem. So anyway, a framework for analyzing this ensemble would let us understand, on the one hand, a framework for analyzing this would let us understand in many ways how these systems work, and let us use that knowledge to improve them. But in general, for just an arbitrary parameterized function, it's not tractable and maybe not defined based on the sort of questions that I was getting before. There's various issues that might come up for completely arbitrary function. But luckily, or what we mostly care about are not arbitrary functions. We care about what are called deep neural networks. And so now that I've sort of highlighted this sort of set of problems that we're going to have to solve, we need to, in order to make progress, we're going to have to actually bring in the particular structure of the set of these set of functions that we're using for function approximation, which are based on these artificial neural networks. And so to do that, let's zoom in and talk about the basic computational unit, which is called a neuron. So I've taken that picture on the previous slide and I've zoomed in on one of these circles, and there's some substructure here. Let me explain what's going on. There's basically two parts. So there's the part that I've highlighted in blue. I guess I have a pointer here up there, which is called the pre-activation. So we imagine in this horizontal direction going to the jth neuron. So imagine that's the jth neuron, and there's a number of lines going into that. So this is a simple function which aggregates the incoming signals, weights them by some number. So each signal, sk, is weighted for the jth neuron is weighted by a number wjk, and then is biased by a number, so that's all summed up, and then that's biased by a number bj. And so these W and B's or weights and biases are going to parameterize how this particular neuron, and then that is fed into a scalar function called the activation function, and produces and I'll give examples of those on the next slide, and either fires or not according to that weighted and biased evidence. And this is kind of a very, I guess, neuroscience-y way of describing these. That's kind of where these functions originally arose from. So to complete the definition of the neuron, we need to talk about activation functions. It's a scalar function and generally chosen to be nonlinear, so that the functions f of x, so that our neural network functions are nonlinear in their input. And so there's an example of some, I don't want to say typical because the one on the left, the step function, which goes by the name perceptron, is not used anymore, although it was a historically important activation function. And the two on the right hand side, the step function times the input, is called the rectified linear unit, or ReLU. That's a very popular one. And then there's also the hyperbolic tangent, which is like a shifted and smooth perceptron. It saturates for large values of its input, and it's kind of linear, or it's linear around the origin. And I actually won't be able to get into it, but today, but it's actually, the analysis that we do actually lets you take many different activation functions and classify them into universality classes that are either loosely based on or not, that include either the middle one, the ReLU, or the right-hand side one, the hyperbolic tangent, although that's, I guess, more of an aside than something I'm going to be able to address here. Okay, so that's the neuron. Then from zooming out a little on that original picture of the network, there's many neurons organized in parallel, and it's useful to talk about them together, and we'll call that a layer. the vector of neurons in parallel. And we can think about this layer as being parameterized by a vector of biases and a matrix of weights. I guess before I was talking about them with their indices fixed as if they were numbers, and now we can think about each layer as being a vector, as being parameterized by a vector of biases and a matrix of weights. And the exciting thing that seems to work really well is iteratively stacking many of these layers to form a deep neural network. And this allows us to create a very flexible set of parameterized functions that are useful for the sort of AI tasks that I discussed earlier. So these two iteration equations define the network. Maybe I should just go back and show that. So this is an example of stacking many such layers. And these, you can get by doing so, these iteration equations define what's called a multi-layer perceptron, which is characterized by the depth and number of such layers and the individual widths of the neurons in the particular layers. This is a simple neural network model that's deep. There are in fact many other interesting architecture choices. For the purposes of the talk, I'm going to focus on this one as kind of you could say a minimal model of deep learning, a model that is rich enough to contain the interesting things that happen when you stack multiple layers on top of each other, but simple enough that we can outlines how the framework works to analyze these models in general. Okay, so and then
Can I ask a question? Can I ask a question? Yeah, so you know, if I think of this as something like statistical mechanics, it looks like the interactions are very non-local.
Yeah, they are. That's right.
Yeah. So is that important? Is that non-locality important?
Well, so you can define ones that have various degrees of locality. Note what is important, and I won't have time to say a lot about it, but the layer-to-layer propagation is local, right? At least in the one that's defined here, right?
I meant spatial non-locality, right?
There's no spatial locality. So yeah, so at some point you could make analogies to I guess certain types of matrix models if you wanted to, right? Where there's you have some cell where everything is connected to everything. Maybe the question then an important question though is whether the ultimate description is going to be k-local in some sense, right? Whether there's a nice description in terms of the statistical mechanics problem, and that's something that I will try to say a little bit about, but that's very important for the analysis. But you're absolutely right. There's no spatial locality, and I think I said this, but there are other models where that's included, but this is it's simpler to not include it from the start. So the point of this slide was just to say that you take the output of the final layer as the function that you're trying to learn. There was a comment earlier about where I responded that actually you might run the output of the function through a logistic function or a sigmoid or something that you might interpret the output of the network as log odds and then convert them into either a label or a probability by a logistic or by taking the max. So if that issue is important to you, then this slide is wrong and I should change it. If not, you can just think about the output of the pre-activation, the final layer as being the output of the function as being the function that you're trying to learn, first being what you would read out to get the output of the function. Okay, so now recalling these three problems, because it was maybe when we first discussed them, things were abstract. Now I tried to make things a little bit more concrete. So I'm not gonna have time to go through how the different analysis works in detail, but I do wanna give at least a little bit of a flavor on it. So in particular, let me think about what you would have to do to find the map from the initialization distribution of the parameters to the initial output of the network. And so what that might look like a little more concretely is that we have an ensemble of initialized networks that are conditioned on the data that we feed into it. And what this ensemble is what this distribution is, so this is the map that we're trying to compute in problem 2, is a joint probability of the different network outputs evaluated on different elements of your data set. And so if, for instance, there's 2 elements, you might hope that after you go through the training process, that if 2 elements of your data set are nearby, for instance, if they're very similar cats, or they're both cats versus if they're both cats, or just very similar in image in the input space, you might hope that there's strong correlations in the distribution of outputs between those between those different data points. So I just wanted to, I've been saying distribution and being kind of abstract about it, so I wanted to be a little bit more concrete. So this is, I'm trying to understand, if you make many realizations of your network function and you feed in your data and then record the different statistics of that, you want to understand the different correlations between all the different data points and all the different outputs across all those different initializations. And so one way of saying across all those different initializations is integrating over the parameters or integrating out the parameters. And so that's what I've written on the bottom here. And this is what I mean by solving a baby version of problem 2, where we start with some very simple distribution to sample from here, and then we're going to end up with a distribution over the outputs of the function of the network at initialization. And I should also add that what is this conditional distribution here? This is the output of the network given a particular parameter and given the data. That's actually a delta function. That's where you plug into this what network you're considering. So for any particular realization of the parameters, if you plug in a particular input, you're going to get a fixed deterministic output. And the randomness here is coming from the fact that you might get a different output for a different way of initializing the function. And we want to understand the ensemble of all this together. So, this is important because specifying this ensemble is going to, let me hold that comment. So once we integrate out the parameters, you can think about the question of which ensemble we're talking about as being characterized by the way we specify the initialization distribution. So if we sample the parameters from a zero mean Gaussian distributions with variances here, I've let, so each bias is independent and has zero mean and some variance that I'm letting depend on the layer. Here, each weight is also independent, and I'm choosing to decompose its variance in this way, which is a nice choice, and letting these numbers, which ideally you want to be order 1, knobs that you use to tune which ensemble that you get. So this specifies which distribution over networks that you're going to get. And so for fixed network architecture and fixed depth, the ensemble, this input distribution that I'm talking about is specified by these. We can think about that in this case as being specified by these 2 sets of hyperparameters that characterize these variances. Why am I harping on this? Oh, sorry, I'll hold that comment for one slide. So one more slide about sort of the flavor of how these calculations, how we might compute this output distribution. Since we have since our network is defined with these iteration equations that iterate us from layer to layer, and as I pointed out when I was asked about locality, that there is a locality of interactions between different layers, we might imagine starting with the joint distribution between 2 layers and trying to factorize it, making perhaps we have some ansatz about what the distribution looks like, and then we can, if we know this conditional distribution, which basically encodes how the one layer is connected into the next layer, then we might be able to integrate out over the pre-activations in the previous layer to get the distribution in the next layer. And that's precisely what we do. One way of kind of thinking about this is kind of analogous to something like a RG flow. So if we have an ansatz for a distribution in terms of what you could call a Euclidean action, or maybe just think about it as a convenient way of parameterizing this probability distribution, and partition function. Basically, what I'm saying is that there are we can write down an action that has some generic couplings that tell us about the correlations of the pre-activations in a given layer. It's going to depend on the data because we want the intermediate variables of the network and also the output of the network are going to take different values according to the data that we put in. And the way we will go a nice way to go and analyze this whole problem is by finding the recursions for the couplings that you would get in this action. Go ahead.
Now I'm confused because I thought by definition you said the initial distribution was going to be Gaussian, but you're writing a generic action for it. I thought you were going to start with the simple one, update it, and say that the updated one would be like this.
Yeah, so I'm sorry because I left out some steps here, but the thing that I said was simple was this P of theta. So the way we tune the weights and biases. But it's not necessarily true. And in fact, it's not true that the actual Z variables, once we integrate over the weights and biases, are going to be simple. So imagine we have a collection of networks and we look at their output and we sample the individual weights and biases. Let's talk about random networks. And we sample the individual weights and biases from this Gaussian distribution because there's this complicated nonlinear iterative set of iteration equations. The distribution that we get of the outputs is going to be non-Gaussian generically.
After you update by a procedure you haven't told us about.
No, even at the beginning.
Hasn't it been trained already, or is that maybe?
No, this is I'm just talking about at the beginning, the freshly initialized networks, but
Z was defined as a linear combination of B and S.
oh, maybe I didn't emphasize this. Z is defined as a linear combination of B and W, but then to go to the next layer, we run it through a nonlinear function in general, and then we apply another scale and shift, and that's how we get the next Z. So to go between Z's, there's a nonlinearity. And even when
So what was sampled from a Gaussian distribution was only the initial Z's in the first layer.
that's right. That's right.
And your general action that you had a moment ago was for the L layer or something like
That's right. And one other, I said something, well, it's fine, but someone might, even if the sigma is even if there's not a nonlinearity here, the product of a number of W's will still give us some non-Gaussianity. So even if the network is linear, if you integrate over the parameters, there's still some non-Gaussianity, but that's just because I said something slightly wrong and I wanted to fix it, but I don't particularly want to harp on that. In general, we should think of it for useful networks for other reasons. The sigma is going to be nonlinear, and these iteration equations are the ones that I'm analyzing. And right, so this action is for a particular layer L, and what we want to do, maybe it's helpful to see this first and then think back here. We would plug this in, and I haven't told you how to compute this, and I didn't want to go into the details of it, but this is actually a simple function. And so by plugging our ansatz in here, we can figure out how those couplings change as we go from layer to layer to layer, and that will let us understand how this distribution evolves from layer to layer to layer. And there's nice analogies to physics that we can say about this. I definitely don't have time to go into them, but I'm happy to chat about it afterwards. I just wanted to put this here to give a little flavor of how the analysis actually works. A couple of things before I return to tell you how this all works out. One important thing about why we care about these ensembles, we're thinking about, well, in general, when you sample the parameters on your computer to make a network, you might think you have one network, but because you're sampling from this ensemble, really you want to understand the whole behavior of the ensemble and then also what's typical. And so to that first point, the mean behavior of the observables actually, and this comes out of the analysis, depend sensitively on these hyperparameters, these biases and rescaled, the bias variances and rescaled weight variances. and the sensitivity generally increases exponentially with depth. And so where an observable, let's say, is like the norm of the first pre-activation, or the norm of the, sorry, the norm of the pre-activation vector. And analogous to notions of criticality, you want to make sure that these knobs are tuned to the point to, finely tuned, to say like the critical temperature here, or the critical value of parameters, for the networks to be useful for training and to perform well at the underlying task. I don't have time to go into the details, but just to give a kind of flavor of why that might be important. If say this parameter this hyperparameter is less than its critical value, then it would be the case that, say, if the observable, let's say, is the norm of the pre-activations, then the norm is exponentially vanishing and our signals don't propagate through the network. And that is going to make training the network or using the network in any way very difficult. And similarly, if if your observable is, say, the distance between two pre-activations, so like for evaluated on different inputs. So for instance, imagine we put one image through the network and a different image through the network, and they're both cats, let's say. So we want them to be, as they propagate through a trained network, we want them to stay close together so that likely we'll be able to classify them together. If the observable is exponentially blowing up, then it makes it very hard for us to be able to classify these images together. So in general, finding these sort of sensitivities to the tunings to the way we specify the ensemble is very important. And we can, in fact, in detail, find these tunings for different activation functions by analyzing the recursion for this quadratic coupling and finding its non-trivial fixed points. And
Dan, could I ask a question?
Yeah.
It's a very interesting point you made, that it sounds like criticality, I understand, is good for initialization, but it's also good for the final stage, like the fully trained network.
Yeah. So it's a bit hard because I don't, or I can't show you the detail, or I'm happy to chat with you about the details of the analysis, but yeah, it turns out it matters for initialization. Then you can use the sort of, if you solve the problems that I discussed, and I'll explain what the solutions look like in 1 or 2 slides, then you can use that to see that criticality matters for generalization, and it turns out to be very important. So the choice of ensemble that you're starting in matters for the ultimate success of what you're doing. There's I guess a related, or that was sort of about the mean of observables across the ensemble, right? This is if you, but and sometimes people do train ensembles of these networks, but often you just want to train one model, and you want your one model to be successful. So we also need to understand the instantiation to instantiation fluctuations of observables. So to make sure that if I train a network and then someone else trains a network, and we use the same procedure, but we sample the parameters differently, we would hope that they still behave, that they're well behaved. And it turns out that the fluctuations, I haven't shown this, but this is, well, so you can either think about these 2 slides, the one on criticality and this one, as being empirical observations that are true, that we then would want to understand, or that you solve the fine-tuning problem by tuning the different knobs until you see something that looks reasonable. And that's in some sense what was done previously for certain models. Or you can think of it, or these are also the outputs of calculations that we're able to do. So in this case, we find that fluctuations typically go like the depth to width ratio of the network. So if you look at a particular layer, lowercase l, then they go like the current depth over the width. And here I'm just simplifying the width by assuming that all the widths are the same. And there's related statements we can make if we care about having individual widths. But what the analysis says is that if we make our networks too deep, then they're not going to be reliable typically. And that also means you can think about that as you may have tuned your ensemble to the critical temperature as per whatever this procedure is, but then the particular network that you get has wild fluctuations, and so it's not well behaved, and it doesn't perform well at the underlying task. And you can begin to understand you can understand this calculation in many ways, but one really nice one is by analyzing the recursion for the quartic coupling, and it's related to the 4-point correlator of pre-activations. So there's a lot more underlying what these results are. I just wanted to highlight them as sort of the sort of things that go into this analysis, and also what you learn about how these functions behave once you do this analysis. To tell you sort of high level what the results are going for particular, or for this model, this multi-layer perceptron model. Note here that since I'm saying that the fluctuations go like the depth to width ratio, that it's very suggestive that something special happens when the depth to width ratio goes to 0. For instance, if we hold the depth of the network fixed and take the width to infinity. And so, in fact, you can analyze these networks in that limit by formally taking this limit and studying what an idealized neural network looks like in this limit. Of course, and this is in literature, this has been known for a while and to varying degrees. For one-layer networks, Radford Neal wrote a paper in the 90s about this, and there's been some recent work for deeper networks. And of course, as a strict limit, it's rather unphysical. You can't actually put, at least in the weights and biases and neuron variables, you can't actually put program a function to have an infinite number of components, but it's a helpful starting point for analyzing what this ensemble looks like. And I guess that's what that bullet point says. In fact, using this limit, we can render these 3 problems that I described completely benign. And again, I don't have time to go into the details of how this works, although if you're interested, I'm either today or please ask me or maybe take a look at the book. But let me just tell you what happens and try to explain how the picture fits together. Also, what time should I aim to end at? 45 or?
We started a bit late, so maybe 50.
Okay, cool. So in this limit, addressing our first problem, which is that there's a proliferation of terms in the Taylor expansion, the higher derivative terms vanish, and we only need to keep track of the output of the function and its first derivative. And similarly, for addressing the second problem, the distribution of these random functions, the two that remain that don't vanish in this limit, are independent. And the marginal distribution factor for both take a simple form. And then addressing the third problem, the training dynamics, regardless of what you do, the way that people normally optimize these networks, the dynamics become linear, but essentially there's only one solution, so the details of the learning algorithm don't matter, and it's very easy to find theta star, the optimal value of the parameters, in a closed form. And so we're able to solve the dynamics problem, and it's only a function of a few things, not everything that we were worried about before. What this is really saying altogether, or I don't know if it's possible to see it from what I just said, but when you put it all together, you find an expression for the fully trained distribution is just Gaussian with a non-zero mean. So that means that what this Gaussianity means is that if you consider training a number of these networks and you take a data point and you push it through, then we'll be able to know what the mean would be in advance. That what the expression, the mean that defines this distribution will be the actual mean you would see if you could perform this, and then also the variance of that distribution would be the variance between the different realizations of the networks that you had when you performed this. So that's kind of what this distribution means. And unfortunately, though, it's a bit too simple. So, and there's a strong mismatch between this theoretical description in this very extreme limit and the way deep neural networks work in practice, and especially the deep part. And perhaps this was hinted at by the way I motivated the infinite width limit by talking about the fluctuations that we're suppressing something that's important that happens with depth. And so, but I guess you can take this as just things that are empirically true. For now, I guess, but the one thing that is observed is that the distribution of real networks do depend on the properties of the learning algorithms used to train them, and that's not the case in this infinite width limit. This is another way of saying is that what this infinite width limit gives you is a particular linear model, or a linear regression. And if time permitting, I'll go into a little more detail what this is if you're not familiar. But a particular type of simple model or that's linear in its parameters, with a special set of random features. And what this means is that these networks don't have feature learning. So they're essentially performing a linear regression with fixed random features defined ahead of time. And that contradicts what is observed empirically about how networks work, and kind of goes against, although I haven't talked about it, a very popular view of what these networks are doing, which is iteratively learning different features of so if we have an image, there's a story that people like to talk about where the input is kind of like the UV. People don't use this language, but maybe this language is helpful here. The input of the image in pixels is like the UV, and then each layer you progressively learn different aspects of the details of the image. So if we're talking about animals, the first layer might learn something about shapes or edges, and then the next layer might learn something about fur, and then the next layer might learn to pick up details like heads or tails, and then finally the final layer might be able to classify what type of animal it is. And this is a very popular story, and there's empirical evidence for that, and these networks don't contain any of that. So if there's something exciting, well, it seems like there's evidence for this sort of heuristic story, and that's part of the special sauce of how these deep neural networks are supposed to work. And so this model is too simple to contain any of that. And really, the problem is that despite even though it seems like we made things way more complicated by adding an infinite number of components, this is kind of playing with the von Neumann quote at the beginning, but basically when we aggregate an infinite number of signals, we're obscuring and washing out the subtle correlations between the neurons in a given layer that might get amplified over the course of training. And so what we really need to do is find a way to put these correlations back and study the interactions between neurons that are present in the realistic finite width limit. I guess maybe because we had the question about the action earlier, I could say that in the infinite width limit for the pre-activations at initialization, the higher order couplings all vanish, and we just have the Gaussian part, and that goes into that's just, you know, that doesn't tell you about the dynamics, but that's one way of seeing what's getting washed out. So we're missing the input that come from these higher order correlations. And the way we're going to do this is by using a 1/n expansion in the inverse layer width. Yep.
Does the statement about the simplicity of infinite width have to do with scaling the couplings so that there is an infinite width limit? Because since each neuron had infinitely many inputs.
Yeah. So
very small.
Yeah. So that's why, right. That's why this n is here. That's what you need to make it work out nicely.
Okay.
This is in so they're all in. So if you imagine squaring this equation, then you have these sums over the weights, and you would use the 2-point function, or you'd use that expression that I just showed you with the CW over n in evaluating that, and that's why you need the 1/n in order to get a nice expression. And there's a couple of places where there's some other hyperparameters I didn't talk about where things like that do matter, and that's important part of the analysis, I guess, from a physics perspective, is understanding the scales. And one of the problems one of the things I hinted at is that there's different things that might get large in this analysis, like the width of a layer and also the depth, and you need to be aware of where they go and kind of rescale different parameters to make that work. No, I think this is where I was. Yeah, okay, so said this, yeah, so we're going to do a 1 over n expansion. Turns out that to make a good match for theory to empirics, we actually only need to keep the first term. Qualitatively, this is it's exactly the difference between a free theory and an interacting theory. So as a qualitative model, it restores, or it brings in a lot of the phenomena that we're interested in understanding. And quantitatively, it turns out, because of the discussion we had about the fluctuations, that actually you really don't want a lot of the other terms to contribute, because then you'll lose the fact that typical networks behave well. So what we want to do is evaluate, understand how this expansion works, and evaluate all quantities at order 1 over n. There's a lot of details in that, and some kind of annoying calculations, but and although I'm happy to discuss the details of them, but given that I now have 5 minutes left, let me just highlight the results. So in this case, rather than having the function output in its first derivative, we have a function output in the first 3 derivatives that we'll need to keep track of, and quantities that involve higher order derivatives vanish as 1 over n squared or smaller. Addressing our second problem, the distribution of these random functions in initialization are perturbative in 1 over n, I guess by setup, and so we can evaluate their deviations from, we can evaluate this joint distribution using the sort of ideas that I tried to highlight before by either studying an action or studying correlations or correlation functions. And so you can evaluate this initialization distribution. And then addressing the third problem, the different training dynamics, or if you use an iterative, if you know what gradient descent is, if you use something like gradient descent, you have nonlinear training dynamics, but you can use perturbation theory in 1 over n, just keeping to analyze them, and you can actually find a closed form analytical solution for a particular network, what the value of the parameters are, which then, using the solution to problem 2, that we have the initialization distribution, gives us the distribution over the ensemble of trained networks. And unfortunately, I don't have time to go into the details of this, but there's some really interesting things that happen which encode the details of the learning algorithm. So you solve the dynamics, but which learning algorithm you use is encoded in that solution. For instance, let me not say the details, but so there's some really nice ways of studying different learning algorithms given these sorts of solutions.
You can take a few extra minutes if you need.
Okay. So, well, there will be a natural stopping point, and then I can ask whether I want to go on or whether people want to hear more or not. There's like a rapid, yeah, okay. So rather than a Gaussian distribution, we get something that's perturbatively non-Gaussian. So it's, well, I don't know what to call it. We call it nearly Gaussian. I guess I didn't really explain why I call this dual, but basically, or maybe it's helpful to say now, by the normal way you might think about implementing these networks on the computer is in terms of the weights and the biases. I kind of think about that as a microscopic definition of the network. It tells you, if you know this list of for a typical state-of-the-art network that has 1 billion parameters, there's 1 billion weights and biases, or billions. And so if you know the values of all those numbers, then there's a very simple description of how to compute that function. But it's not telling you, that's why people think it's black box, because you have all these numbers and you're not really sure why you're doing any of these individual computations the neurons are doing. In this description, we've integrated out the parameters, so we don't have the billions of parameters. And in fact, we have a very sparse description, and all we need is to know what these different couplings are, and the couplings have very nice interpretation in terms of the correlations of data after we put it through the trained network. And there's a nice story about parameter count, or about how you think about this description as simple, even though there's a large number of parameters, and when to use this description, when to use a different one. But this, I guess I could also say that this limit is the one that's relevant for the sort of, well, actually, let me hold that point for the next slide. The final point, that's a natural stopping point, although there's one other point that I want to make after this, but important byproduct of this analysis is that we can actually start to understand what's important about having a deep neural network, about stacking many, many of these layers. to the question before about scaling different things and keeping track of what's getting large or small, if we consider a deep network, and the ratio of the depth to the width of the network becomes very important. And in fact, anything that that's important with depth is going to need to have some depth to width ratio that's not equal to 0. So in other words, we can think about this notion of infinite width versus finite width as also being very related to shallow versus deep. And so, in the strict limit where the aspect ratio R goes to 0, we're turning off the interactions. And so if we're, this is essentially answering, if I have a network on my computer, how do I know whether the infinite width description is good, or I need to use the finite width description, which seems to be more in line with what, with how deep, sorry, let me try that sentence over again. If you have a network on your computer and you keep making the widths wider and wider, you obviously can't make the widths infinite, but you might want to know, when is the infinite width description good? And obviously it's going to be good to the extent that this depth width ratio is going to 0. So, but if you do that and you have that ratio going to 0, then even though you might think you're studying deep learning, you're not. These networks are not really deep, and they're relative, as the relative depth is 0. And similarly, if you have a regime where the depth to width ratio is small enough, you can incorporate these non-trivial interactions, but the effective description truncated order 1 over n is going to give an accurate accounting of the fully trained distribution, and we call these effectively deep. And then in the regime where the depth is large compared to the width, then the neurons are strongly coupled, and the signals propagate will behave chaotically, and there's large fluctuations, and these networks are not really useful, and in some sense they're overly deep. And the main point is that networks of practical use are going to have small aspect ratios, so they're going to be, but non-zero, so they're going to be described by this sort of nice description that I was trying to that I was overviewing before. So yeah, I can, the thing that I want to do next, which maybe I can go through quickly or take, I'm 5 minutes over. Okay, I wanted to contrast, I'll try to do this quickly, so I apologize if it's too quick, but I want to contrast deep learning framework with maybe a familiar framework, which is linear regression. And linear regression is basically what I referred to before as a linear model. So this is the simplest. You can think of this as the simplest machine learning model. We just have a bias and a weight, and so it's a linear transformation of the input. And so this, as I've written here, this model is linear both in the input and in the parameters, but the linear and linear model takes its name from the fact that it's linear in the parameters, not linear in the input. But we can fix this not linear in the input really easily. Sorry, the fact that it's linear in X means that it can only approximate functions that are linear transformations of the input. We can fix that really easily. Oops, I have to go through this in order. By instead of just putting X there, we can use some nonlinear transformation of X before we scale and shift it. And in this context, you have to know something about the data that you're trying to model, about the function that you're trying to learn. And if you have that information ahead of time, then you can put that into these 5 functions and then succeed at the modeling problem. Here I've just deleted the bias by subsuming it into the files. It's kind of unimportant, but this slide, if it seems complicated, it should be familiar. For instance, if we want to learn a one-dimensional function that we think is cubic, we might pick a basis that is a constant and up to cubic, polynomial basic up to cubes. And so substituting that in, we would have a function that looks like this. So now we're able to learn a cubic polynomial and do linear regression, which I assume many here are familiar with, but we introduce some way of determining whether our model is close to the underlying function that we want to learn. This is finally, I got to the concrete idea of a distance function that was asked about earlier. Here, why I'm probably not going to use it again is just, so I probably should have just used f. The true is the observed values of the function, and we want to make sure that our model is predicting values that are close to the observed value. This is sometimes called the mean squared error or square loss. And in this case, because it's linear in the parameters, or because the model is linear in the parameters, this quadratic, the loss is quadratic in the parameters, and we can just simply take a derivative and set it equal to 0 and find the minimum that way. And you can think of this sort of procedure, which you can write down the solution in terms of inverting some things as a naive version of a learning algorithm. So what I wanted to, the reason for going through this, well, there's two reasons, but the main reason is I want to compare the frameworks of this linear models to what we talked about in deep learning and try to make a point that this is kind of new and interesting and different, but also explain to like concretely point out how they're related. So linear regression goes back to Legendre and Gauss, and so it's probably unlikely to be, it's hard to imagine that it's useful for these sorts of AI tasks. Otherwise, it wouldn't have taken to us, it wouldn't have taken so long for us to be able to solve these AI tasks. So the first point is that the three problems that I outlined are tractable, and you can analyze them completely. I guess hopefully that's obvious. I probably don't have time to go through it, but you might say that this is just curve fitting, and so naively, it's unlikely to be useful for like the more complicated AI applications. And so what I wanted to say is that deep learning extends this classic paradigm in two important ways, namely by introducing nonlinearities in both the input and so it's nonlinear in both in the input and the parameters. So even though we talked about how linear models can be nonlinear in the input, here you don't have to specify what basis of phi's that you're using from the start. Instead, you might use certain nice properties that you know about the data to design a particular network. And for whatever reason, or maybe not for whatever reason, but this is more analogous to this sort of design is much easier to find nice phi's than it is for having to pick a basis of functions. Going back to the much used cat example, for the case of that, I wouldn't know what basis of phi's to use, but you might use ideas like translation invariance of the data to design locality in the different neurons that you're using, and that implies some basis. But in order to know what the basis is, you have to do the sort of analysis that I've outlined here. So you start with some network architecture that an engineer can play around with and design, and that implies some basis of phi's that are complicated and not something that you would have just written down. And then the second point that I discussed I discussed earlier about what infinite width networks don't do is that the effective notion of features evolve over the course of training. So this is due to the nonlinearity in the parameters. And so it's really no longer just fitting a curve with a fixed basis, where it's no longer the case that you just pick the basis ahead of time and then have to hope that you did a good job and solve the linear regression problem. Here, you actually, when you have a nonlinear model, you actually get you can actually interpret what's happening as the model is learning features over time, like that story that that heuristic story that I told about how deep learning is popularly expected to work. And this is only a property of nonlinear models. So the final, I could stop here and that's sufficient. There's a simple model, a nonlinear model, where I was explaining kind of how it works. That's those 3 slides, or I could just stop here. So whatever.
This might be a good place to stop.
Great, thank you.
Let's type that.
It's really only take 10 minutes.
Any questions for Dan?
Yep.
This was a great talk, thank you. So a number of the observations, and you sort of hinted at this along the way, you made have been floating around in the deep Gaussian process literature, and I was wondering if you could sort of say a little bit about the connections.
You're talking about
the aspect ratio and effective kernels.
Yeah, so I think most work is focused on the infinite width limit from and understanding sort of different properties, but I think there's some work in particular cases for particular activation functions and maybe limited numbers of inputs about understanding the depth width limit but not like a general way of understanding that for many inputs. That's my understanding of that. Nika and Hannon is one. Other questions? Yep.
So once you have your solution of your distribution function of whatever the dual theory is, does it help understand something about an actual neural network in the world where I have some set of W's, and weights and biases, and you can look at it and say this is performing well or not performing well or something?
Yeah. So there's a number of things you can learn. One is various calculations can tell you how to set the different hyperparameters or ways that we're selecting this ensemble. So some of the notion of criticality or suppressing the fluctuations, right? You can use those details to try and improve the networks in practice. And there's calculations that connect that you can connect that directly to how networks ultimately perform, like how well they generalize. And so setting those is one thing. I think, and that's what I would say to a practitioner. And some of the work that we're doing now is precisely in that. And what's also true is if you have a different architecture that you care about, you can go and do the full set of analysis using this framework, but you can also use this framework to tell you which observables to measure and how those relate to quantities that you might care about. So there's sort of hybrid approaches that you might use practically. But kind of what I think is more interesting is that these models, fit in a larger class of like these nonlinear models that I was trying to talk about, which do different things than we might be useful. So like this model is just a linear model deformed with a quadratic term, something that's quadratic in the weights, and it behaves differently than sort of these classical statistical models, and like that multi-layer perceptron on the network that I was talking about for most of the talk is like a cubic. Is like a cubic model. So the more minimal one is this quadratic one. But what I find exciting about this is that we can begin to ask questions about like, how are the networks representing? How are they learning? What do their features look like? How does it take the data to learn features and sort of questions like that, both either in the real models, like there's an expression for what is the solution in that. It's kind of gross because the phenomenology of like the real network is a little gross, but even in these simpler settings, we can sort of isolate the exciting things that deep networks are doing, understand how they work, and then in principle use that to build other different better networks.
Dan, this is Tom Banks. I'm on Zoom. I have a really naive question. So there's a way to do minimization problems where you set up a Boltzmann distribution with your forcing function, and then you do Monte Carlo basically to minimize that and lower the temperature to find the true minimum. Could you sort of concisely explain why these kinds of models do so much better than that?
I don't know that I can concisely explain that, but I guess, so in the infinite width limit, I think you would get the same solution. That would probably be a bad way of going about it. For the finite width limit, for these nonlinear models, you get different solutions depending on what the learning rate, or sorry, depending on the learning algorithm that you use. And in principle, I guess you could take that learning algorithm and you wouldn't do Monte Carlo. I guess you would just analyze the full Boltzmann distribution and understand what solutions are implied by that, and hopefully that understanding those details would tell you why one is better than another. I guess though, so that's like the maybe conservative answer. The less conservative answer is that I think that the way these the way you want to train these networks, and I didn't really talk about this, but they're typically set up so that they have way more parameters than data. So it's in this limit that you might have thought doesn't, like if you think about fitting with the polynomial basis and you know, as you let the degree of the polynomial equal the number of data points, you have these wild and crazy turns due to some sort of fine tuning problem. There's a reason, or well, it turns out that that's not a generic thing that happens. And these models want to live in this or perform best in the space where there's more parameters than data. And what you want to do in those situations is actually take the training loss to be zero, or you know, train them until the training loss is zero. So my guess is that the problem with what you outlined is that the temperature is finite, and that maybe and I would also guess that in the limit of beta going to infinity, and you know, the zero temperature limit, that might reduce to some other learning algorithm. I don't know what it would be because I haven't thought about that, but that's my guess for why that probably doesn't work as well. That makes sense.
Thank you.
I have a question also on Zoom. So why did you assume the action had a Z2 symmetry? The action is a function of the Z's. Was that just for simplicity?
Why did I assume it's a function of the Z's? Is that what you said? Z2
no, why did you assume it has a
yeah, that's implied. The Z2 symmetry, the even reason is implied by the zero means of the parameters. So if you look,
I see. So that wasn't unnecessary.
Right, so like if you imagine just taking an expectation of a Z of this equation, I guess is the most generic one, right? The fact that we have zero mean is going to mean that the 1 point function vanishes and so on. And so that's where that comes from. The train, remember, this is here for simplicity. I was talking about just the marginal distribution of the output at initialization. The full problem, you have to care about the much more grand statistics. And you know, for the train network, it doesn't output zero. It outputs something that, you know, depends on the labels of the training data that you have. So the means are not zero, and that's also secretly why. Or let's not see. There's a number of reasons why I just talked about initialization here, but it does make this simpler.
So I also had I always have a general question about AI, which is how do you guard against bias in the choice of training data?
How what against bias?
How do you guard against bias in the choice of training data?
Right. Yeah. So, well, this analysis is so I guess one way of thinking about what I talked about is not analyzing the data generating distribution. Like there's some joint P of X comma Y or P of X comma F of X distribution, right, that we're getting samples from. I just said that we have a collection, we have a data set. It's, you know, and the calculations that we did here, you can think of as kind of like what we do when we analyze this, you know, a scattering problem in collider physics, right? We have some theory or we have some description, and then we want to figure out how to relate that to observables for some fixed description. And so in this case, what I'm fixing is that someone just handed me some data. But what I can say is that this, you know, understanding the solution, let's say, so that, you know, so if you have a particular network, right, there's an expression in our book, it's kind of gross, that tells you what function your trained network is outputting up to L over N, you know, to the order that our expansion is valid. That's fine, you see there. And so by looking at that expression and understanding it, you can understand exactly how the data is being transformed. And so I guess you might hope, and maybe a simpler way to do it, that's why I was going here, maybe a simpler setting to do it is the thing I didn't have a chance to talk about, but a more minimal model of representation learning where, you know, the linear model is probably too simple, but for a minimal model of representation learning, which is capturing some of what the, just stay here, capturing some of the details of, or some of the ways in which the network is learning representations, the way it's building features from the data. So by analyzing a model like this, you might understand what like statistics of the data set are how they're being used and how they're being transformed. And that might be a useful way of understanding how these models are developing biases given some data set. But I don't know how to think about the data sets themselves. That's like a separate question. Yeah.
This might be a good place to stop. Let's thank Dan for a really wonderful presentation.